This is from Chapter 22, Problem 5, which reads, Atomic physicists ignore the effect of gravity within an atom. To see why, calculate and compare the gravitational electrical force between an electron and a proton separated by 10 to the negative 10 meters. The charges and masses are given on the inside back cover. So, to just make hopefully a quick drawing, here maybe a proton. There we go. Okay, it wasn't supposed to be empty, so I'm just going to make it filled here, hopefully. There we go. Okay, and now I'm going to make an electron, and maybe I'll make it green, filled. There we go, and here it is. And each one of them has a certain charge. In fact, the proton has a charge of 1.6 times 10 to the negative 19 coulombs. And I forgot one little thing there. Charge of the proton equals plus 1.6 times 10 to the negative 19 coulombs, and the charge of the electron is negative 1.6 times to the negative 19 coulombs. And the mass of the proton is what I look up in the back of the book. I want to say 1.67 times 10 to the negative 20. Yep. 1.67 times 10 to the negative 27 kilograms. Here I don't need a plus or a minus because masses are always positive, and then the mass of the electron is 9.1 times 10 to the negative 31 kilograms, roughly 2,000 times smaller than that of the proton. Okay, these two masses here, because of their mass, they attract each other gravitationally, so we have a gravitational force between the two, which is attractive. And of course it's the same either way, because the law says that gravitationally I have Fg equals gravitational constant mass of the proton times mass of the electron divided by the distance between the two squared, and that distance is given in the book as 10 to the negative 10 meters. So D equals, what is that, 1.1 billionth of a meter. There we go. So 1 times 10 to the negative 10 meters is the distance. So there's a gravitational force between the two, and as I said, it's the same for either one of them, because this can be turned around here, so both of them experience the same force. That's also in accordance with Newton's third law, the action-reaction principle. Of course, it's the electron that experiences a larger acceleration because of its much smaller mass. Okay, they're saying that, well, we have to compare this with the electric force. I'm just going to write there Fg, and the electric force is the Coulomb force between the two, so Fc equals K times Q1 times Q2 divided by D squared. There we go. And therefore we're going to have a Q1, I'm sorry, an Fc, and they say that in the problem here that they imply, or let us show, asking us to show that the electrical force between the electron and the proton is much larger than it is for gravity, and so I make that error larger. It's not to scale, it's actually so much larger that I wouldn't be able to put it on paper here. In this case here, it's attractive because there are of opposite charges. The force still is the same, the Coulomb force is the same for either one of them, because again I could turn these around, and because of the action-reaction principle, and again the acceleration between the two is the acceleration between the two is larger for the electron because it has a much smaller mass. Okay, if this was the attraction here, then the electron would just fly into the proton, but so to say, take this with a what is it, salt of grain or grain of salt, the electron, so to say, is orbiting, so it has a forward momentum here, a relatively large one, and the force here is, oops, I didn't mean to draw this here. The force here is a deviation from going forward here in its momentum, and therefore it will get into an orbit around a proton, so to say. There is more to it when it gets to that level. But we have enough information to do the calculations, so I'm gonna plug in the numbers. Okay, I actually could go, well, I could go back a few times, but I'm just gonna start it over. So 9 E9, or as I showed earlier, 9 times 10 to the 9th times, and this one here would be 1.6 10 to the negative 19. And because it's the same for either one of them, for the electron and the proton, I can put that also in parentheses and square it. This only works for the Coulomb force because in this case, oops, in this case both charges are the same, and then I divide that by the distance of 1 times 10 to the negative 10 meters squared, and I come up with 2.3 times 10 to the negative 8th, so 2.3 times 10 to the negative 8, and the units are newtons. And then I do the same for the gravitational law, so it's going to be 6.67 10 to the negative 11 times the mass of the proton, 1.67 10 to the negative 27 times the mass of the electron, 9.1 times 10 to the negative 31, and at this point you can already see that's going to be much smaller because I'm comparing negative 31 and negative 27 to the negative 19 twice here, and those numbers are quite a bit smaller, and the gravitational constant is much smaller than the Coulomb constant. Okay, anyway, divide by 1 10 to the negative 10 meters squared, and I come up with 1 times, or 1.0 I believe, times 10 to the negative 47 newtons for the gravitational force. And we can see that the electric force is 39 orders of magnitude larger, 10 to the 39, so 1 with 39 zeros, and I came up with that by comparing negative 8 to negative 47. So if you write out this number, it would be a 1 with 39 zeros behind it. That's how much larger the Coulomb force is than the gravitational force, and that justifies that the gravitational force between the proton and the electron can be readily neglected compared to the electrostatic attraction. Okay, here I made a little animation, proton and electron, and let me show you. So here's the electron, 9.1 times 10 to the negative 31 kilograms, and here it's charged, negative 1.6 10 to the negative 19 coulombs. Notice that the electron at this point here doesn't have any velocity, so I'm going to keep that 0, which means that there's really, the electron is not going to orbit here. The proton I just anchored down, so it's not going to go off the screen. It may do very slightly move. Anyway, here's the mass of the proton, 1.67 10 to the negative 27 kilograms, and the charge, positive 1.6 10 to the negative 19 coulombs. And the way I start this out with is that I turned electrostatics off, okay, and I turned gravity on in such a way that they're not going to fall down, but that they attract towards each other. It would be called planetary, except it doesn't have a speed to begin with, so they're really slamming into each other. Okay, one of the things I have to do in my animation is the accuracy, and that means, for example, here I tell it give me one diagram every 120 seconds, so calculated every 20 minutes, so it's relatively slow what the electron is doing. It needs a lot of time in order to do something. So here it's just a gravitational attraction between the two. I hit the run button, and this would be here after 2 minutes, 4 minutes, 6 minutes, 8 minutes, 10 minutes, 12 minutes, 14, 16, 18, 20 minutes, 22, 24, 26, 28, half an hour, 32, 34, 36, 38, and so on. So you can see that this tiny distance, which is written, by the way, down here, 1 times 10 to the negative 10 meters, it takes half an hour just to get the half distance of the proton at a billionth of a meter. Okay. Anyway, in respect to that, I'm going to get to electrostatics in just a moment, but I need to drastically, before I do that, I need to drastically change the timing here, and I'm going to change it in such a way. This is the number I remembered. Let's see, 19, and then when I click somewhere else here. So here what I'm going to show is one image every 10 to the negative 19 seconds. So it's really fast, the time here, really fast. You get an image every gazillionth of a second, okay? And I still have it on gravity, and notice that one diagram after another, you're not going to see anything. I mean, this would take you forever, and I mean in the neighborhood of eternity, to actually get to half an hour, because I made the time here so fast, 10 to the negative 19 seconds, that it needs to add up a lot of diagrams in order to actually get to half an hour where we actually can see what happens to the electron. So gravitational attraction between these two here is very small. Okay, let me reset it, and let's go over to turning gravity off, turning electrostatics on. There we go. And double checking the accuracy, so it's just as fast. There we go. And now I hit the run button, and notice under electrostatics it moves very fast within this gazillionth of a second, which tells us that the electrostatic attraction is much larger than the gravitational attraction. For the gravitational attraction, I need to be in the neighborhood of 10, 20, 30 minutes in order to actually see something. Here it's a gazillionth of a second, and we already see quite some attraction here electrostatically. If this is all that would happen, then the electron would just slam into the proton. That's not the case. So I'm going to give the electron a certain initial speed, which I calculated on the side as being, or so I thought I had it written down. Oh yeah, on my calculator, as 1.59 times 10 to the 6 meters per second, roughly 1,590 kilometers per second, or roughly 1,000 miles per second. And of course, it has only a very small radius, so within 1 second it makes billions of orbits. And again, I have the time here really fast, so at a really small number, and when I hit the run button, you can see the electron orbiting nicely. My time here is so fast, that means at such a small time difference from one diagram to the next that we actually can see it orbit around, just like a planetary orbit, except this one here is due to electrical attraction. Notice earlier I turned off gravitational attraction. So this whole thing here was just the animation connected to the problem that I discussed of comparing the gravitational to the electrostatic force.